In this video, I want us to take a look at the impact of the learning rate on our learning curve. And by the learning curve, what I mean is these figures that you see here. Basically, it's just the plot of how your loss declines over time. I mean, how the loss is supposed to fall as the number of epochs increases, and how your accuracies are also supposed to rise as the number of epochs increase. And so we want to investigate how the learning rate impact the ability of the perceptron to learn. Okay, and before we start, I want to remind you, if you have not subscribed already, please click the subscribe button and click the notification bell so that you get alerts whenever I publish a new video. And I hope you're enjoying it so far. Okay, so one of the arguments that we pass to the train function is LR, which is the learning rate. And by default, we have set it to 0.01. If you remember from the previous episode, I mentioned that the learning rate controls how frequent we make changes to the weight and biases of our neural network. And in this case, I mean the perceptron. I also stated categorically that it is a value between 0 and 1. And in our case, we have set it to 0.01 by default. What it means is that when you call the train function, you are able to pass in a new learning rate that is going to control how often we update the weight and biases. And the line of code that indicates that we are actually using the learning rate to control the frequency and the magnitude of updates are on this line. Okay, you see that we multiply the update. So to calculate the update, we multiply our error by the learning rate. So what it means is that think of it as a proportional scale. Okay, so if your error is big and you multiply it by a small learning rate, you are actually making fewer updates. And if your learning rate is high, which is 1, the maximum number, then you are making more frequent updates to your weight and biases. And so in this video, we just want to investigate how the value you choose for your learning rate impacts the ability of the perceptron to learn, and also how many epochs you need to train for to be able to get a good enough accuracy. So on this line, when we call train, we didn't pass any learning rate. I'm going to run this cell again, and you can see that after 50 epochs, our accuracy is 1 on the test set and also 1 on the training set. Now let's try to lower the epoch. So LR is equal to 0.0001. Let's run this and see how it impacts our perceptron. So you can see that we are making less frequent updates to our weight and biases. And so at this point, yes, it is performing well on the training data, but it hasn't learned enough generalization power to perform well on new data sets. So if we go ahead and then plot figures, you can see that indeed the test set is below the test accuracy is below the training accuracy. Let's go ahead and do one more run, and this time I'm going to reduce the learning rate to 0.00001, and let's see what's going to happen here. So at this point, you can see that after 50 epochs, our train accuracy is only 52%, and unsurprisingly, our test accuracy is also only 44%. What it means is that we are making less frequent changes to our weight. And so at a point when we have done 50 epochs, it is not enough number of epochs for the weight adjustment to begin to plateau, for the perceptron to have learned well enough the patterns that are hidden in our training data. So if we go ahead and we make a plot of this, you can see that our loss is, it doesn't seem like something that is actually falling, and I'm sure once again it's because of the scale. And you can see that our train accuracy is just 44%, and it doesn't seem like something that is rising. And our test accuracy 44, and our train accuracy is only 52. So one thing you can do is, if you set a lower learning rate, then intuitively it means you are making less frequent updates to your weight and biases. And henceforth, when I say parameters of your perceptron or neural network, I am referring to the weight and biases. I want to stop having to say weight and biases, so that I'll just say parameters. Okay, so if our learning rate is this low, one more thing we can do to ensure that our perceptron will learn well enough is to increase the number of epochs, because with a small learning rate, we are making fewer and less frequent changes to our perceptron's parameters. Okay, so I'm going to increase this to, let's say, 200, and then let's run this. So you can see that after 200 epochs with a learning rate of 0.00001, our training accuracy is 98% and our test accuracy is 96%. So we can come down here and we still have a loss of 1, which means there is still more learning that the perceptron can do. So if you look at this plot here, you can see that it fell from 35 all the way to 1, and our train accuracy rose from almost 51% all the way to close to 100, which is at this point 98, and then our test accuracy is at 96. So as long as you are not satisfied with your test accuracy, what you can do is to increase the number of epochs, or so you basically have to tune both number of epochs and your learning rate, and this aspect of deep learning is known as hyperparameter tuning. So a hyperparameter is any parameter that is outside your perceptron or outside your neural network. In this case, the only parameters that are inside our perceptron are the weight and biases, and the other things that we tune. Think of hyperparameters as knobs that you tune to control how your neural network learns. Okay, so I have seen that 200 epochs is not enough at this learning rate. So what I can do is go to 300, and this is the point that I keep reiterating. You can see that at with 300 epochs at the same learning rate, we are able to reach accuracy of 1 or 100% on both train set and test set. And then we can go ahead to plot our graph, and you can see that we are making a 0 loss and our accuracy is also 1. At this point, what it means is, if you increase the number of epochs and you keep your learning rate low, there are chances that you will still converge to a global minimum where your accuracy on both the test set and the training set are good enough. And once again, this is a verification of how stochastic training is. So I ran it again, and at this point, it is not converging. It is converging, but it is not performing well enough for what I want. Okay, so with this learning rate at 350, I'm still getting 92% accuracy on the test set. So you can see that the practice of deep learning is more of an art than a science. Okay, there aren't formulas that is going to guide you as to what learning rate you should set. You learn these things through heuristics, you learn them through practice and experimentation. And you can also see that the accuracy on the test set also affects your decision region here. So you can see that, of course, because the accuracy on the test set is not good enough, you can see that the line is missing some of the points that are supposed to be in the blue region and is actually plotting them in the yellow region. So what you have to do is you have to keep training, and then you have to keep modifying either the number of epochs or your learning rate up until the point where you are satisfied with the performance of your neural network, like in this case, when we are getting 100% accuracy on both test sets and the training set. And you can see that if we come down here and we plot the decision region again, we expect that this line will be placed properly in the middle, that separates the yellow region from the blue region. So thank you very much for watching. Don't forget to subscribe, and I will see you in the next video.